I'm Bonnie Harrison and welcome to The Details Long Read. Today, a story from the July-August edition of New Zealand Geographic magazine called Weaponised. And if you're not comfortable hearing about strange appendages on male animals, look away now, because this is about how evolution is an arms race. With each generation, predators and prey refine their aggressive weapons and defensive armour, writes Kate Evans. If you pick up a current copy of NZGeo, you can also see the fabulous illustrations that go with this story, done by Giselle Clarkson. This is Weaponised by Kate Evans. Every summer, giraffe weevils converge on dead and dying trees in the New Zealand bush. While the females painstakingly drill holes into the rotten wood to lay their eggs, the males jostle for the right to mate with them, resulting in some truly medieval jousting matches. A male giraffe weevil can reach 90 millimetres in length, towering over the smaller females. His ridiculously long snout, or rostrum, makes up half of his entire body and is fringed underneath by a fetching moustache. With eyes at one end and mouth at the other, the oversized rostrum is a terrifically impractical face extension, most of the time. When another male attempts to steal the weevil's woman, the snout becomes a ruthless weapon, a lance he wields to flick his rival off the branch and out of mating contention. The New York Times once dubbed this battle style snout walloping. Two major forces drive evolution, and both sometimes result in animals developing over-the-top weapons. When interactions between predators and prey drive adaptations, we call it natural selection. Here, if a particular mutation helps a creature survive until breeding age, it's more likely to be passed down. Sexual selection, meanwhile, generally results from competition between individuals of the same species over mating rights. In his book, Animal Weapons, The Evolution of Battle, American evolutionary biologist Douglas Emlen explains why it is mostly males that fight. It's all down to the size difference between sperm and eggs. In every species, eggs are far bigger. The discrepancy is most extreme with kiwi, which have the largest eggs relative to their body size of any animal. But even in humans, an egg cell is 10 million times the size of a single sperm. Making eggs requires both more energy and more time than making sperm. Most female animals therefore produce fewer reproductive cells, but invest more in each one and take longer to recover between births or batches of eggs, Emlen explains. Males, on the other hand, produce trillions of sperm and have a much shorter sort of turnaround time. The disparity means females have more to lose if a breeding attempt fails, so it makes sense they tend to invest more in protecting their offspring. It also explains why males must often fight, or give the impression they can win one, if they want a chance to mate. The simple fact is that in virtually every animal species, there are nowhere near enough eggs to go around, writes Emlen. The result is competition. In some species, males race to impress females by developing ornaments. Think of a peacock's jewelled tail, the flanged face of an orangutan, a proboscis monkey's fleshy nose, or even a man's beard. In other animals, though, these perennial contests have led to the evolution of a wide range of weaponry: horns and antlers, spurs and tusks, poisoned fangs and overgrown canines. The giraffe's long neck evolved not for eating, but for fighting. And so did the giraffe weevil's lance-like rostrum. The bigger the snout, the better a weevil's chances of winning a fight, defending a female, and passing on his genes. That's the simplified story, But nature loves exceptions. While most female deer lack headgear, reindeer of both sexes grow antlers every year. Males shed theirs in early December, after breeding season fights are over. Females retain theirs for another month, says Ted Stankiewicz, an evolutionary behavioural ecologist and director of the California State University's Mammal Lab. That means they can dominate the males to gain priority access to food while they're pregnant and breastfeeding, and implies that, given the time of the year, Santa's sleigh is being pulled by female reindeer, Stankiewicz says. Female jacanas, North American wetland birds, have evolved formidable bright yellow wing spurs they use to fight with other females. Why? Well, once a female jacana has laid a clutch of eggs in a certain male's territory, he takes care of them until and after they hatch. While it takes around 3 weeks for a female to produce her next batch of eggs, the male is out of action for 3 months or longer. At any given time, therefore, more females than males are ready to mate. So they fight each other for the privilege. In the world of insect battles too, things are more complex than they first appear. Male giraffe weevils aren't all finger-long, lance-wielding behemoths, says University of Otago behavioural ecologist Chrissy Painting. I've found no animal in the world that is as variable at a single life stage, she says. The smallest males are fully grown at just 15 millimetres, around the size of your thumbnail, and sport just a tiny rostrum. They obviously don't stand a chance against the big guys in a fight. The human equivalent would be a normal-sized man squaring up against a giant 10 metres tall. During Painting's doctoral research, she discovered the little males use a totally different mating strategy. Biologists call it sneaking. Weevil congregations can resemble a crowded party, where the bigger males are busy mating, defending females, and fighting with other large males. In the chaos, there are often opportunities for tiny males to sidle in alongside the females and begin mating with them unobserved. A clear case of see no weevil, hear no weevil on the part of the oblivious alpha males. If the jocks do catch a sneaker in the act, Painting says, you can almost see the confusion. They waggle everything and throw their heads around, and then they try and yank the little one off. Small males have a strategy for that too, Painting says. I call it swinging. They tuck themselves around under the female and hang on for dear life, all while continuing to mate. Sneaking behaviour has evolved many times across the animal world, and lots of heavily armed species feature small males that break the rules, writes Emlyn. Dung beetles are a particular favourite of biologists, as they've evolved a spectacular array of horns. In some species, they face forwards, in others backwards. They protrude from the head or sometimes the thorax. They can be single or double-pronged, have branching tines like an elk's antlers, or be absent altogether. In at least one species of dung beetle, horned females fight each other for access to cowpats, which they feed to their young. The Ornithophagus nigroventris dung beetle is native to East Africa, where it makes its home under piles of elephant dung. The female digs a tunnel and snuggles with her eggs inside, while a so-called major male crouches inside the entrance and defends it in a series of single combat fencing matches with his massive pointy horn. But there's a trade-off. The nutrient-intensive appendage makes up 30% of his body weight, leaving him with dodgy eyes and stunted reproductive organs. Minor males, on the other hand, never develop horns at all, so they have plenty of spare energy for growing huge testes and producing extra sperm. In addition, their unencumbered faces enable them to dig their own tunnels under the dung. They sneak in, mate with a female under the nose of her hulking guard, then slip away. It's a risky strategy, but when it works, The small but virile male can make the most of his opportunity, proving that for dung beetles at least, technique can trump size. Brute force is all very well, but the most powerful biological weapon of all is chemical. Venom is basically evolution on acid, says Brian Greig-Fry, a biologist who heads the University of Queensland's Venom Evolution Laboratory. Its poisonous proteins evolve faster than any other, he says, and venom itself has separately appeared more than 125 times across the animal kingdom. There are venomous bats, insects, snakes, lizards, scorpions, spiders, sharks, fish, octopuses, jellyfish, and even a primate, the slow loris. Venom is used for offence, defence, and in mating contests. During the breeding season, wrestling male platypuses stab each other with their venomous ankle spurs, causing a paralysing pain that can also harm humans. A veteran soldier who was jabbed when he tried to rescue an injured platypus in North Queensland in 1991 reported that it hurt much worse than his wartime shrapnel wounds. For predators, venom is a fast and powerful tool for subjugating difficult prey, Fry says, so it makes sense it's appeared so many times. But how exactly does it evolve? There's no intelligent design theory that goes, poof, have another toxin. They have to take the toxins from somewhere, he says. Venom glands are very leaky, he says, and occasionally express random proteins. A protein that happens to have a damaging effect on an animal's prey will give the predator an immediate advantage, making the trait likely to be passed on and amplified over generations. For instance, the venom of Australian elipid snakes, like taipans and tiger snakes, contains massive amounts of factor XA, among many other compounds. This protein naturally occurs in vertebrate blood and aids clotting. But when a taipan bites a bandicoot, the venom floods the unfortunate creature with an overdose of factor XA, beginning an irreversible cascade of blood clotting. It turns on everything, everywhere, all at once, says Fry. That leads rapidly to a massive stroke, and it's all over for the bandicoot. Death is just a side effect. The main advantage for the snake is that the prey is immobilised. Other venomous animals achieve immobilisation via completely different pathways. Proteins in scorpion venom block chloride channels in its prey's muscle cells, making them all flex at once. Death adder venom also affects muscles, but in another way. It contains a neurotoxin that blocks receptors on the cell's surface, stopping messages from the nerves getting through. You've basically cut the internet, says Fry. You never get the instruction to make that muscle move. Cobra venom, on the other hand, contains both sedative neurotoxins to subdue prey and painful flesh-eating cytotoxins to repel the snake's own predators. The wild diversity of powerful compounds in animal venom makes it fertile ground for drug discovery. Captopril was isolated from the venom of a type of Brazilian pit viper half a century ago and is still widely used to treat hypertension. But it's not such good news for those unlucky enough to get envenomated, as scientists call it. Every bite or sting must be treated differently. Effective antivenoms do exist for many types of snake. The reptiles are relatively easy to keep in captivity and to research, though Fry has learned the hard way of the need for serious PPE. Not only has he survived multiple snake bites, he also developed a deadly allergy to certain kinds of serpent simply by breathing in traces of their powdered venom in the lab. But some of Australia's other poisonous creatures are more problematic. Jellyfish suck, says Fry. It's like working with highly emotionally unstable snot. purifying the proteins inside the mucousy venom is technically very difficult, meaning scientists still know hardly anything about the deadly box jellyfish and the even more horrifying irukandji jellyfish, a marble-sized, transparent dot of ruin whose stinging tentacles cause not only extraordinary morphine-resistant pain, but an impending feeling of doom so intense that people who are stung by one often suffer PTSD. If they survive, that is. Nature's weapons can resemble daggers, clubs, maces, swords, spears, lances, poison, tear gas, or armour. The armament of choice is influenced by the fighting arena and opponent, and whether it's used for offence or defence. Studying the evolution of deer, Stankiewicz found that the males of almost all species have either tusks or antlers. Tusked deer, sometimes called vampire deer, are more ancient and live mainly solitary lives in deep forest. Biologists call these slinking species. You can imagine that if you meet up with an opponent in a dark alley in tight quarters, you want a little dagger. You want to slash, stab, and run away, he says. As the slinkers ventured out onto the plains, they dropped the tusks and began to evolve horns and antlers. If your weapon can be seen from a distance, you might not need to fight every time and can avoid unnecessary injury, Stankiewicz says. One group of deer, though, remains stuck in the middle. Muntjacs hail from Asia and have bizarre facial scent glands that they turn inside out when excited. Males fight dirty with their tiny tusks and stubby antlers, a munt jack of all trades but master of none. Other animals use weapons for predator defence. Think of an echidna's spines, a skunk's stinky spray, or an armadillo's armour. Comparing 3,000 species of mammals, Stankiewicz's team figured out that those most likely to have defensive weapons were middle-sized and lived in open habitats. Mammals under 1 kilogram can generally blend in and hide. Those larger than 10 kilograms are too big for most predators to handle. The ones in between are big enough to be seen and to make a juicy, attractive meal. Natural selection has weeded out the weaklings, so we're left with mid-sized mammals that can fight back with tooth and claw, curl up into a ball of spines, send jets of foul-smelling liquid shooting out of their anal glands, or are rabbits. Hopping is a much faster form of escape than running, Stankiewicz says. There's no free lunch in evolution, and building a suit of armour from scratch takes a lot of energy. Pangolins, porcupines and armadillos have therefore compromised in the smarts department, says Stankiewicz. More armour equals smaller brains, he says. When your defences are that good, though, it doesn't really matter. He says, you can sort of lumber around and not have a care in the world. In the animal world, as in geopolitics, the most awe-inspiring weapons are used more often for deterrence than actual combat. Skunk's spray is so effective against mammalian predators that only owls will dare attack them, and since the strongest, healthiest buck antelopes grow the biggest headgear, a male can tell at a glance if he has a chance against a rival. They only fight when they're so evenly matched that they can't tell who's the better fighter, says Stankiewicz. Some male harvestmen, which are spindly, long-legged arachnids found in New Zealand forests and caves, also show off their strength and vitality with elaborate headgear. They're blind, so they have to suss each other out by touch. And instead of antlers, they have highly exaggerated chelicerae, a pair of articulated fangs similar species usually use like cutlery to help shovel food into their mouths. Chrissy Painting examined harvestmen in a miniature CT scanner and found that their chelicerae vary dramatically both within and between species. Some are long and skinny, others powerful and chunky, and they're often embellished with a species-specific array of fussy bumps and knobs. Scientists have never seen harvestmen mate, she says, but they have seen them fight. They tap each other's chelicerae, which sometimes escalates to grappling on the ground in a big jumbly mess, she says. To Painting, the diversity suggests these sorts of weapons, those used in sexual combat between members of the same species, are designed for intimidation, not killing. She says, you don't actually want to get to the stage of a fatal fight. That's really dangerous for both animals. Instead, she thinks, the intricacy enables sparring males to quickly gather information about each other and decide whether to step up or back down. She says, like, oh gosh, he's big, and he's got all these little teeth on him. If weapons were just about inflicting harm on your opponent, you wouldn't see the amount of variation that we actually see, because selection would have operated to find the perfect weapon. Extreme evolutionary pressure can result in extreme innovation, as the harvestmen brandishing their crazy-ass chelicerae show, says Painting. These structures are arguably pretty stupid if you're thinking about survival. They're really unwieldy, they're difficult to carry around, they make the whole body lopsided, she says. But like the giraffe weevil's ridiculous snout, the fact they exist at all suggests they serve a critically important purpose, giving a male more chances to mate. As Stankiewicz puts it, weapons teach us what evolution can do. That was Weaponised, written by Kate Evans and published in New Zealand Geographic Magazine's July-August issue. The Details long read is supported by the Public Interest Journalism Fund. We'll be back next week with another long read. Ka kite anō.